Hello and welcome to another two video series related to networking. In these two videos, we're going to look at network performance measurement. And in particular, we're going to focus on a tool called iPerf, or really iPerf3. And we'll dig into a little bit how to use the tool. It's a relatively popular tool. Certainly people like Jeff Geerling, or if you watch Serve the Home or Lawrence Systems, it's used in a lot of videos. And it's a very popular tool for looking at the available bandwidth on a connection and for diagnostics in a bunch of different network things. So it's a very popular tool, and we're gonna kind of dig into it a little bit and show some ways to use it, some ways that it can be a little bit misleading sometimes, a few ways that it breaks, and hopefully you'll leave with maybe at least one thing you didn't know. So if there's something you learned in this video, then please put it in the comments. So we're going to talk about iPerf3. So before we go to iPerf3, a little backstory on that that's quite interesting. So there was a number of tools in the history of performance monitoring tools for networking, an original one called TCP, and that tool had spawned off many tools, one of which was an original tool called iPerf. And that tool was developed and had some use and then sort of stalled a bit with no one really doing active development on it. And along came two different distinct groups of people, and one group of people decided they wanted to bring that iPerf back to life, but they wanted to do it by rewriting it. And that's the iPerf3 side of the equation. And so they rewrote iPerf from scratch, and part of the reason was to make the code easier to understand. The original iPerf code is a little messier, I think. And they made it originally a single-threaded, so a pretty straightforward, easy to follow a bit of code. And they modeled it after the previous iPerf in terms of the commands, the interface, the way it worked, but rewritten. And so that's iPerf3. Then sort of at the same time, closely, someone did decide to revive the original iPerf code and start working on it again and doing bug fixes and enhancements. And that became iPerf2. And so iPerf2 and iPerf3 are both in active development. And they are two different tools, yet they're based from the same formula, and so they're very similar. If you saw the output from iPerf2, you might mistake it for iPerf3 because they're very similar in many ways. There are a few differences in the code base and a few differences in features. I think maybe iPerf3 is a little more commonly used in the Linux world, I think, at least from what I can tell. And I've used iPerf3 for a long time. It may in part just be because people assume when they hear iPerf3, that must be the newer version of iPerf2, even though they're very independent things from each other. And so we're going to focus a little bit on iPerf3 and how to use it as a tool and what it can do. There are a couple other things about iPerf3 that are interesting. One is that, as far as features, they're very similar, iPerf2 and 3. There is one particular feature in iPerf3 that I like, and it somewhat, I think, helps the popularity. It has a design in it where when the client connects to the server, it can tell the server, hey server, I want to do this kind of test. Can you get ready and let's do that kind of test? And the result is that you can generally run the server side of iPerf3 without any options and just leave it running. And then clients can connect to it and request or do different kinds of tests. And that's a little different than iPerf2. In some cases, iPerf2, you have to stop the server and relaunch it with some different options. But with iPerf3, it effectively can be configured remotely by the person connecting, the client connecting, to do different kinds of tests. And in fact, when you try to install iPerf3 on most Debian distributions, one of the options during the installer is it asks you if you want to install it as a daemon. So have the iPerf3 server running in the background all the time. And that's in part possible because you don't really need to tweak it much. You don't need to change command line options very much. So it's possible to run it as a daemon. In fact, you could run it on all of your Linux boxes and have it always there in the background and then be able to quickly run a performance test against any one of those servers at any time. And so iPerf3 has some advantages in that. It's probably a little easier to do. Someone could turn on the server for you and leave it running for a week, and you could do many different types of client tests against that server without any more interaction. So it's got some cool advantages to it. I think perhaps the most negative or known negative thing on the iPerf3 landscape really starts with a knowledge base article that Microsoft put out last year, so in 2024, where they basically said don't use iPerf3 on Windows for anything high performance because it doesn't work well. And the blog post was a technical blog post and went over a couple different things. One was simply that iPerf3 is not technically supported on Windows, and so it doesn't release Windows builds. And there are some people who have released Windows builds, but they were pretty far behind in versioning. That is somewhat fixed now. There's someone now who's releasing regular Windows builds as the latest version, so that's, I would say, a more solved thing. The bigger part of the article had to do with the fact that iPerf3, it is a Unix utility written to use Unix socket interfaces. And so to compile it on Windows, they use Cygwin, which is a library that looks like Unix to the application and then back translates to all the Windows APIs. And Cygwin is fantastic and makes it possible to compile many things from the Unix world into Windows. But it does add a little bit of overhead in that translation from the Unix socket side to the WinSock side. And then even more so on the Windows side, to get truly fast network performance, there are some different paradigms, things like I/O completion ports that you wouldn't do on the Linux side, but you would use on the Windows side to do very, very fast socket communication. And so in that regard, it is true that iPerf3 is not super optimized for Windows. That being said, you can certainly, and I've used the Windows version, and it does in fact work. I think I do occasionally see performance issues. That the amount of issues you see does vary a little bit based off how fast your network is compared to how fast your CPU is. So there was a period of time where maybe you had a Sandy Bridge CPU and a 100 gig network, and that wasn't a good match. I think a modern high core count, very fast processor is now pretty far ahead of the capabilities of a single network interface. But you still can have problems on Windows with performance. And also I think that there are some open bugs with the Windows UDP. I think the multi-threading doesn't work, if I remember correctly. So there are a couple of glitches there. So in general, it is meant a little bit more for the Linux Unix side of the house as a tool. But other than that, though, it's a great tool to use. And so today we're going to go over to the system and take a look at iPerf3 in a little bit of detail and do some different kind of cool testing and explore things. And then the second video, we're going to delve into a very particular interesting behavior of iPerf3 as it relates to aggregated links, which is a really cool and it's kind of just an interesting thing to think about. So for now, let's head over to the computer and take a look at iPerf3. So let's take a look at using iPerf. So to start, on one machine here, we're going to run iPerf3-S, which means run it in server mode. As I mentioned in the intro to this, the iPerf3 supports in server mode listening for what kind of test to do. So it really gives you good control on the client side to decide what to do. So this is another machine. These two machines are connected to the same switch. And we can run iPerf3-C and the 117.3. So that's the IP of that machine. Hit enter, and away you go. And iPerf3 by default does 10-second tests, so it'll print out once every second. And then at the end of 10 seconds, it'll give you a little summary of what happened. So a couple things to keep in mind. So you see we're getting 940 megabits a second, which is about right for a 1 gig interface. So when you're looking at this output, a couple of really important things to know. The first thing is this output here. These are from this side, from the client. The client's saying, this is what I'm doing. Then at the end, it prints a summary from the sender, which in this case is the client. And then it asks the other side, what did you see? And it prints what the receiver said that it saw. And it's important to note that iPerf3, by default, this -C client mode, it's an upload test, not a download test. So it is uploading, it is sending to the server from the client. And many people might expect it would be the opposite of that, but it is in fact sending from the client to the server. If you want, you can add -R, which says let's do the test in reverse, which has the client tell the server, you send to me. And so it makes a TCP connection, and then it has the server side send to the client side. It'll run through 10 seconds of testing here, and then eventually at the end, it'll spit out what the receiver, which is this client, saw, and what the sender says that it sent. And with TCP, because it's a connection-based protocol, both sides will generally agree on what was transferred. The bit rate can vary a little bit based off how they do the accounting of time spent from the start to the end of the test. But the receiver side is the really most important thing to look for, because this is what the other side other side ended up seeing as a result of the test. So straightforward, remember that the default is sending, which is upload. You add -r, makes it receive for download. You can also do -c 10.1.17.3. You can do -dash by dir. And that says we want iPerf3 to do 2 connections. And in one connection, it's going to send from the client to the server. And the other, it's going to send from the server to the client, and do them both in parallel. And in a situation like this, you see we get reasonably close to equal speed on each of the 2 directions. And it summarizes to 937 and 939. You might lose a tiny bit of bandwidth because in a single direction test, the other direction, which is where the acknowledgements for TCP come across, is unloaded. Of course, doing bidirectional, both directions are fully loaded, and you also have to squeeze in the acknowledgement. So there's a tiny bit of overhead there. So you might notice a difference there. This will make a huge difference in wireless, because if you do an upload test in wireless, you're sending from the client to your AP. If you do a download, you're downloading from the AP to your client. If you do the bidirectional, you're doing both at the same time, and the airspace bandwidth is a limited quantity. And so when you're transmitting and receiving at the same time, there is a collision there of the total amount of bandwidth available in the airspace. And so you will definitely see lower numbers. So the bidirectional is a good thing to try. It's good to do all 3 and see how it varies from send to receive to bidirectional. But all of this involves using TCP, which works really well. One thing to be aware of is if you do TCP and you do a connection, in this case, this is a very low latency connection. These 2 machines are connected to a single Cisco N9K switch. So that's very, very, very low latency. If these were farther apart and they had high latency between them, same bandwidth, but higher latency, you would notice when you run this test that the first 2 or 3 seconds, the bit rate will typically be lower. And that's a result of the way TCP does a thing called slow start, and the way it figures out how much material it can put out on the wire before it hears back an acknowledgement. That has to do with the window size. And TCP will try to optimize that. It'll try to figure out what that optimal window size is, but it takes a little bit of time to do. If it's a low latency network, it's almost instantaneous. And you can see here, it made no difference. In a high latency network, you might notice that the first 2 or 3 seconds are kind of warming up the connection. And there is an option called -O, which means omit. And you can say omit the first 3 seconds of the test. And one smart thing is when you do this, you can see that it basically restarts a test after 3 seconds passes. And then it runs it for a full 10 seconds. So it'll now do basically 13 seconds of testing, but give you the result. And the important thing is this summary down here is just over those last 10 seconds. It allows you to skip the warm-up interval in the TCP connection and not have them counted in the statistics. So it's a valuable thing, more so on connections that are really high latency. So this all works great. In general, using TCP is really ideal because it will attempt to do the best that it can in terms of what the connection can support. And it generally results in pretty good measurements. But there are some use cases where that isn't true. And so iPerf supports UDP. You can add an option -U, and you don't need to change anything on the server because the server side is sort of self-learning based off of what the clients ask for. So you can put in /-U and hit enter. And when you do that, you'll be amazed at the amazing bit rate of 1 megabit per second. And the reason that you see 1 megabit a second is because in UDP, the client side is doing the UDP sending. It's up to it to decide how fast it wants to send. It can attempt to send as fast as it wants. And so with UDP, you need to tell it how fast you want to attempt to send. If you give it nothing, it defaults to 1 megabit. And it's honestly, it's a good, simple test. It tells you that the UDP traffic is working. But another thing with UDP that's very important is these numbers here. These represent what the client is trying to do. It has no reflection on what really happened. It's what the client tried to do. Then down here, you can see that the sender, that's us, the client, we sent 906 datagrams with a total of 1.25 megabytes of data. The most important line is this second line, which is this is what the other side actually got. So sure enough, it got all 1.25 megabits, not a huge surprise. It also gives you the average jitter, which is the variation between arrival times. And most importantly, this 0 right here means there were no lost datagrams from the sender to the receiver. So when you're looking at the test, it's very important that you might run a test and be chugging along here, and these numbers are spitting out fantastic numbers. But then you get to the end here, and the number here is terrible, and that tells you that you were trying really hard here, but it wasn't making it to the server and into the server's iPerf queue. And that'll be really important. It'll become evident here. We're going to do a few tests that will kind of expose more about this. So you can do an option called -B, which is you can tell it, hey, I want you to try to send this fast. So we could put in 500 megabit and say, okay, I want you to try to send at 500 megabit. And sure enough, it has no problem modeling that and doing it pretty accurately. And so it's sending at 500 megabit. And of course, the server is receiving it. And there you go. It finished, and the server says, yep, I got everything. No problem at all. I got every packet you sent me. The transfer rate was as expected. So we can raise this up to maybe 930 megabit. And of course, now it's going to attempt to send at 930, and you can see it has no problem sending at 930. And the receiver side, as happy as can be, it's sending at 930. Everything looks great. Lastly, you can also do -B0, which just says hit it as hard as you can. And that tells the client, in this case the client sending, to transmit via UDP as fast as you can. And sure enough, it will attempt to transfer as fast as it can, 957 megabits, so we're pretty close to the maximum transfer rate of that connection. And it worked great. There were no lost packets. Both sides saw the same amount of data being sent. But there are a couple of gotchas here, so we're going to try this again. If I go over to the server here, and we're in screen here, I'm going to run a stress test, just going to load the machine a little bit. And we're going to do the same test again. So now we're sending, and look at that, it looks beautiful, 957, 956, we're feeling good, it's just hammering that interface. But wait until the end, and the hint is right there. We sent at 956, but the other side only received at 482. It dropped 400,000 of the 825,000 packets. They were lost somewhere along the way. And I mention this because even if I go over here and I stop this stress test, sometimes you can do this test between two relatively quiet machines that are not busy. These are directly connected to the same switch, so really no other potential bottlenecks. And you will occasionally run this test and get 1, 2, 5, 10 lost datagrams. And you'll be asking, well, how is that possible? And it's important to understand that the sending side is sending as fast as it can, effectively very close to line rate. And those frames are arriving in the switch, and the switch then looks up in a table where it's supposed to go, what port it goes to. And there's generally a queue in the switch that it puts the queue into to be sent from the switch down to the network card on the other side. But on the other side, the network card then has a driver that retrieves that data, puts it into some type of queue, and eventually the iPerf program pulls from that queue. But if something happens on the sending side, the machine itself is in an interrupt handler for longer than normal, or something pauses the machine just very briefly, that buffer that's in the driver will almost certainly be full all the time. And that means that next packet's going to show up. And when a packet shows up from a network interface into the driver, and the driver looks at the buffer and the buffer's full, it drops it. Very simple. And so you will occasionally see, even in a network where it's perfectly tuned, that you occasionally have these dropped frames because they're being dropped in the network stack of the receiving side. This can also happen if I did a test where I had two machines, each connected to a switch, and those two switches were connected to another switch in the middle. Because in that case, if that link, say the link from one of the switches to the middle switch was a little bit busy because of some other traffic, you may be sending faster than that downlink can downlink, even just for a brief moment. And the switch in the middle will eventually run out of buffer room and drop frames. So you should expect that to happen. If you're doing UDP testing, you're going to see frames that get dropped. And one of the ways of debugging is figuring out where and how they're getting dropped and eventually why they're getting dropped. But it's an important thing to always remember. With UDP, you've got to look closely at these last two lines to figure out what exactly happened. Did it really transmit the number of things that you thought it did? And so, we're looking pretty good here. The UDP test works really well. We're getting very close to the line rate. So let's try something new. Let's go back to TCP. And let's switch interfaces. So we have another interface between these two machines. We're going to run that, and you can probably guess it's a 10 gig interface. And getting pretty good bit rate, 9.4 gigabit per second, which is about on par with what you'd expect over a TCP connection on a 10 gig link. So this worked beautiful. I mentioned this retry column here, which is a statistic provided by the OS that iPerf collects that indicates how often something was put into the queue to be retransmitted, but it doesn't actually mean it was retransmitted. When it gets put into the queue, there are reasons where an acknowledgement could show up and then it doesn't get retransmitted. So it isn't precisely the number of times a given packet was retransmitted, but it does hint at acknowledgement didn't quite show up in time, and so we're put this in a queue to get retransmitted, and it's possible that it did or didn't. The only way to know for sure would be to look at the statistics on both sides and see how many actual packets were transmitted, or you can packet capture and see that as well. So this is an indication of a little bit of throttling somewhere, but these are relatively small numbers. And so it doesn't indicate anything tremendously important. But if those numbers were very large, it would indicate that while TCP is doing its job perfectly, it's probably retransmitting a bunch of frames, which then translates eventually to lower overall bandwidth. So TCP, that works great on this connection. Let's switch to UDP. And as I mentioned, sorry, I'm not paying attention here. There we are. Okay, let's go back to 21. So UDP, and we'll pick a bandwidth of, let's do 1 gig. Pretty simple number. So we'll do 1 gig. And of course that works perfectly. It's a 10 gig connection. You wouldn't expect anything less than that. And remember, with TCP, we got 9.4. So let's try 5 gig. So we're going to try to transmit at 5 gig. And right away, you're like, huh, that looks a little weird. We're not even able to transmit at 5 gig. This is what we're trying to do. And of course, those of you over here will look that we got even less. Not all the frames showed up. We lost 4.7% of the datagrams between these two machines as a result of sending here at 5 gig. I mean, you weren't even able to send it at 5 gig. So you're immediately thinking, well, but TCP did 10 gig or almost 10 gig without any problem. And there's a very important distinction. If you go back to a normal TCP test, and we put in, oops, sorry about that, 21, and we put in -v, it will tell you something really interesting. I'm going to stop it here, right here. It says starting protocol TCP, 131,072 byte blocks. And what that means is that iPerf3 creates 128K chunks of data, and then it calls into the OS to put that in the queue to go at IP, and then builds another 128K, calls into the OS and puts that in the block into the queue to be sent. So every time you're doing a system call, you're giving 128K for it to go, parse, and put into this TCP queue. And the actual IP layer will take that 128K, break it up into datagrams, so they're based on the size, the MTU of this network, all of that. It handles all of that, eventually figures out how to get all 128K across the connection to the other side. And so when your iPerf3 is talking to the operating system, it's doing these big chunks of 128K. If we do -u, and we can do any number here, we can do 1 gig, doesn't make a difference. With that -v, look what you see here. The byte block size is 1448. And that number is what iPerf3 thinks the MTU of this network is, which is accurate. So it knows that this network handles 1448 byte datagrams. And so it is calling the operating system, however, for every one of those 1448 byte chunks of data. So when you try to send 5 gigabytes of data or gigabits of data, it's calling into the OS a tremendous number of times to do that. And in fact, I can show you a command here. Let's see here. So if we do, let me pull this up here. Okay, so let's go back over here. So we can run the same thing, and this is going to do iPerf3, and this is going to send 1 gigabyte of data. And so it says, sure enough, we sent 1 gigabyte data. This is over TCP. And it says, well, we did 11,000 system calls during that time while we were doing that test. So it took 11,000 system calls to do that test. Now, if we do the same thing, but we make it -u and -b 0, go as fast as we want. Let's see what happens. This is going to do UDP. And so UDP, we transferred 1 gig. Actually, we didn't even get all 1 gig transfer. Some of it failed, but we were close. And now we made 747,000 system calls. And again, it's because there's a system call for every one of those 1,400 and some byte frames, as opposed to sending 128K at a time. So the default in iPerf3 is relatively CPU intensive on the UDP side, because of course every one of those data frames is being sent individually into the kernel. Now there is we use the word hack. There is a flag you can set. I think it's -L, yeah, which says, we can do this here. So that says to iPerf3, well, instead of sending 1,400 byte datagrams, try sending 32K datagrams. Now I'm going to hit enter here. This is going to run, and it will, you can see it says here, warning, UDP block size 32K. And that's looking pretty good. It sent, that's because 1 gig there. Yeah, so that worked fine. It sent over the interface, and you'll notice there was far less datagrams sent. If we were to count the number of system calls, there'd be far less system calls. So this effectively worked pretty well. But if I make this be 0, so we're going to hammer the network, you will see some very unusual bad behavior. So this is looking great. We're sending at 9 gigabit a second, 9.4, so we're really hammering the interface. The number of datagrams is relatively small, so it looks great. But look what happened on the client side. It didn't really get anything. It only got 9,000 datagrams total. It's a loss. And if you watch over here, it started to work, and then it just fell off a cliff. And the reason is a peculiarity in iPerf3, which is that when you tell it to use a window size, it creates a block of data of that size, and it puts a little header in that block that says, hey, iPerf on the other side, here's a 32K block. This is block number 7. Here's the block. And then it'll label the next block. The next 32K block is a different number. And on the receiving side, it's looking for these 32K chunks. The problem is when you do -B0, you're almost certainly going to get some datagrams being lost. And when you do this test, this 32K, it's true that iPerf3 calls into the kernel and says, kernel, here's a 32K datagram, please send it. And what the kernel does is it goes, great, it looks at the network interface. The network interface has an MTU of 1,448, and it breaks it up, it fragments it. And so the network stack will automatically fragment and break this into little pieces. And the problem is a couple pieces get lost along the way. So on the other side, when it goes to reassemble this 32K magic packet, it's missing pieces and it doesn't know what to do. And so it loses sync and then stops working. So the use of this window size or block size with UDP is relatively difficult to do. Because the fragmentation will make it such that if you lose one thing, you'll lose the entire sync. It doesn't mean it can't be done. If you do it at lower bit rates, and you don't lose a lot of frames, it'll work. But be very aware that using that as a way to get around this problem of so many system calls, that doesn't work as well as you might think. So an important distinction is that if you use the UDP tests, the number of system calls can be massively higher. And so if that's a bottleneck, which it often is at higher bit rates, it can be a little confusing because TCP may show a fantastic transfer rate while UDP shows it being a little bit weak. One other thing is we'll do 1 gig. So this makes sense. We're going to do a 1 gig UDP send, and of course that works as expected. But let's try this. Let's go back to 0 here. And if I do 0, that goes as fast as it can. It does this 4.5. We're going to go change to a different interface. So 20. And watch this. Now we're getting 7 gig. All I did was change to a different interface. And this interface, we're able to get 7 gigabits per second. And look over here. It received that much. And it only lost 248 of the almost over 1 million datagrams sent. So that worked really well. And so you're wondering, well, what's the difference? And the difference is very simple. Let's look here. So if you look at this interface, the 20 interface has an MTU of 9,000. So this has jumbo frames turned on. This interface does not. And so this demonstrates that one of the advantages of jumbo frames, particularly with iPerf, is that since iPerf ends up sending, and if I do -V here, you'll see it, it sends the blocks into the kernel based on the MTU of the network. When you have jumbo frames, you can send bigger blocks in single datagrams, and so it cuts down the number of datagrams sent into the kernel, in this case by a factor of probably 4 or 5, and so it makes a big difference. Now we still didn't get 10. We're peaking out here at 7, and so there's another option in iPerf called -p, which is parallel, which is do more than one thread of this thing. And so we can say, let's do 4 threads. And now it's going to have 4 threads running, each one hammering as hard as it can. And sure enough, you see that each one is getting 2.5 gig per second, but totally 9.93. So that is like right at the very limit of a 10 gig interface. And look at that. On the other side, it worked perfectly. Few lost frames there, 517 out of what, 1.3 million. So about what you'd expect in a network like this. So the parallel option, doing more than one connection, can make a huge difference with UDP. You also could say, let's have each one send 1 gig, and then have 10 threads do 1 gig each. And now each one's going to attempt to do 1 gig, and they get pretty close to that. And you max out at that 9.93, which is very close to the theoretical maximum. And so the parallel option is a great option. And you can do the same thing with TCP. So we can take off all the UDP stuff and say, let's do 10 threads of TCP. And it'll open 10 connections, and of course they're all going as fast as they can. And this ends up being 9.90, so relatively close to the UDP speed. A little bit of overhead for TCP, not a ton. But in some cases, though, the parallelization option can help quite a bit, because these threads can often run on different cores or different CPUs. And there are some really weird behaviors to be aware of here. If you get to lots of threads, if you get to more threads than there are cores, then you get this thing where it kind of jumps between the threads, and so you see these weird oscillations in the bandwidth. And even here, you notice that sometimes it was a little slower, and some threads had a better bit rate than other threads did, just based on contention. Sometimes the thread's running on the CPU that the other CPU from the PCI Express bus that the Ethernet card's on. There's lots of kind of interesting interactions there. But the use of P is a great thing. And if you run a test, you should generally run it with a single thread and see how it does, and then run the same test with multiple threads and see what kind of improvement you get with more threads. And you might discover that the limitation is in the sending side or anything like that. So it's a great set of tests to know and understand. So when you're doing testing, people often start with TCP. Be aware of the directionality, which is using both forward, reverse, and bidirectional. And then you can use UDP to dig in a little deeper and maybe see if things are getting dropped. And maybe how they're getting dropped. And of course, you combine this with something like NetFlow or some way to look on a switch and see the statistics for a given interface. You can then see maybe where things are getting dropped. Are they getting dropped in the client or in the server? And hopefully these little tips here will help you make the best use of iPerf3. There is a whole nother set of really cool things about iPerf3 and networking and related to LACP lag groups. And we're going to go over that in the next video. There's a lot of cool things there, some interesting complications about using iPerf if anything in your network has aggregated links with LACP or any aggregation algorithm. There's a lot of really weird, cool behaviors that can happen in that. And so we'll dig into that in the next video. So if you have any questions at all about this, don't forget to put them in the comments and let me know. And hopefully, if you've been using iPerf for a long time, you at least learned one thing from this video. Thanks for now.